Hello, my name is Colin Berry. I am the team lead for the Mizzou Student Underwater Robotics Foundation. As well as being the team lead, I'm also the mechanical lead. So that's why today I'm going to be talking to you about RoboSub Jelly's propulsion system. So for RoboSub this year, we decided to go with a compact but very maneuverable and fast propulsion system. So that's why we decided to go with the vectored ROV with 4 vertical thrusters. This configuration allows us to have 6 degrees of freedom and a lot of thrust in every direction. So if you look at our horizontal thrusters are configured in a way that allows us to yaw or move in any direction. So this allows us to both crab walk in order to have precise movements and use our gripper mechanism, but also allows us to go fast in our forwards direction or yaw in order to reorientate ourselves. If we go to our vertical thrusters allow us to pitch, roll, and sustain the depths that we need to. So this allows us to orient the robot in ways that make it advantageous for us to do the tasks, or just control our depth, get down to the right tasks at the right time. So overall, this configuration gives us the capabilities both of going fast from task to task and of the precise movements that we need in order to go from task to task. So overall, this helps our competitive strategy because we want to maximize the amount of points that we can get for all of our tasks. So for going through the gates, it's really easy to get the style points, since all we need to do is turn on all 4 horizontal thrusters in one direction to yaw 360 degrees. And our vertical thrusters, we just need to orient in different directions on each side in order to get the 360 degrees of roll. So we're able to get those style points. It's easy for us to follow the lines on the bottom of the pool because with our downwards facing camera, we're able to see where the line is pointing and essentially crab walk our robot along the lines to ensure that we know exactly where the robot is going, that the robot can follow the lines really easily. So the robot will just follow it in one orientation and then switch orientations without yawing, so that we can follow that line super easily and effectively. In addition to that, it's easy to swim fast hydrophone tasks. And then once you get to tasks, it can be really precise. So it can get to tasks super quickly with the amount of thrust that it has with all these rotors. And then once you get to a task, it's able to do precise movements like lifting up the top of the box. It's able to grab onto it and then just change its depth in order to lift the top off. So we don't need to have a moving arm mechanism in order to do the task that we need to. We just need to use our robot and its degrees of freedom capabilities in order to perform the tasks, which makes our other subcomponents super easy to design and a lot more fail-proof. So the testing that we've done with this sub, we haven't been able to get it into the water very much. So we haven't been able to test its in-water capability. But as far as theoretically testing it, we've been able to test above water on our test bed. So we just have a little like board set up in our build room with all the thrusters on it that we're able to test. So we're able to run some code on it, but it's it's in the air, so we're not sure how it'll act in water. So if we look at this graph, because our thrusters are at 45 degrees, if we're going straight, we're able to put all of those thrusters up to full capability, to the full voltage, so that it is able to go a lot faster in the forward direction than it is at any other direction. So if you look at this graph, we're able to go fast at the 0 degree direction, the 360 degree direction, and the, we're able to go fast at the 0 degree, 90 degree, and 180 degree. And this is because that is where the robot is able to use all 4 thrusters at the same time. So it's able to go fast, the fastest in this direction, this direction, this direction, and this direction. So knowing that, we were able to find a way to make it go fast with pitching. So we were able to run a simulation on this with the pitch angle. So this is assuming that the robot is going at that 0, 90, 180, or 270 degree directions. So we input the force of buoyancy that our robot creates to ensure that we aren't tilting it too much that the sub won't be able to hold its depth. But once we do that, then we're able to see how far that we can pitch it. So this graph was created with a buoyancy force of 10 pound force. So once we're able to figure out that buoyancy force, we're able to see how far we're able to pitch it. And as you can see, with 10 pound force, we're able to pitch it about 0.82 radians and get up to a thrust of 71.7 pound force from the original 43 that we can get in any one direction if we're just going horizontal. So this configuration allows us to both do super fast movements in the XY direction, as well as go even faster if we pitch. And so yeah, that's why we chose this design. And the configuration that we chose for our propulsion system really helps out in the challenges. So yeah, thank you.